Hello, AP students. In our last lesson, we learned how to draw Lewis structures. And so now we will use this understanding of drawing Lewis structures to determine the molecular shape. So this lesson, which is found in our text in section 8.13, will be discussing a model that we will use to visualize and determine the shape of the molecule. That model is called Vsepr. Vsepr stands for valence shell electron pair repulsion. And what it does is it shows the structure being formed by minimizing the electron pair repulsions. So the electrons want to be as far apart as they possibly can. Okay, so the steps to understanding and using the Vsepr model are basically this. You draw the Lewis structure for the molecule, then you count the electron pairs and arrange them in a way that minimizes the repulsion. That means puts them as far apart as possible. Okay, and you determine the position of the atoms from the way the electron pairs are shared, whether they're being shared or whether they're lone pairs. And then you end up counting these pairs either being shared or not shared, and then from there you determine the molecular structure. And what I will do is I'll insert a clip to show you how to do this. Okay, now the following slides are incorporating video clips that show different molecules with differing amounts of pairs of electrons. So as you watch the video clip, pay attention to the whole repulsion idea, pay attention to the shape that forms, and then also pay attention to the bond angles that you see between the different pairs.
The structure around a central atom is determined principally by minimizing electron pair repulsions. Two bonding electron pairs around the central atom result in a linear structure. Carbon dioxide has a linear structure. The bond angle for a linear arrangement is 180 degrees. Three bonding electron pairs around the central atom result in a trigonal planar structure. Boron trifluoride has a trigonal planar structure. The bond angles in a trigonal planar arrangement are 120 degrees. When one of the three electron pairs surrounding the central atom is a non-bonding pair, as in sulfur dioxide, the resulting structure is known as bent. Four bonding electron pairs around the central atom result in a tetrahedral structure. Methane has a tetrahedral structure. The bond angles in a tetrahedral arrangement are 109.5 degrees. When one of the four electron pairs surrounding the central atom is a non-bonding pair, as in ammonia, the resulting structure is known as trigonal pyramidal. When two of the four electron pairs surrounding the central atom are non-bonding pairs, as in water, the resulting structure is known as bent. Five bonding electron pairs around the central atom result in a trigonal bipyramidal structure. Phosphorus pentafluoride has a trigonal bipyramidal structure. The bond angles in a trigonal bipyramidal arrangement are 90 degrees and 120 degrees. When one of the five electron pairs surrounding the central atom is a non-bonding pair, as in sulfur tetrafluoride, the resulting structure is known as seesaw. When two of five electron pairs surrounding the central atom are non-bonding pairs, as in chlorine trifluoride, the resulting structure is known as T-shaped. When three of five electron pairs surrounding the central atom are non-bonding pairs, as in xenon difluoride, the resulting structure is known as linear. Lone pairs of electrons take equatorial positions preferentially. 6 bonding electron pairs around the central atom result in an octahedral structure. Sulfur hexafluoride has an octahedral structure. The bond angles in an octahedral arrangement are 90 degrees. When one of the 6 electron pairs surrounding the central atom is a non-bonding pair, as in bromine pentafluoride, the resulting structure is known as square pyramidal. When 2 of the 6 electron pairs surrounding the central atom are non-bonding pairs, as in xenon tetrafluoride, the resulting structure is...
Okay, so you saw in this clip several different molecules with differing amounts of electron pairs, some bonding, some not bonding. And what you want to do now is notice as you watch the clips and they walk through and explain the molecular shape, notice that lone pairs tend to have a greater repulsion than bonding pairs, and therefore giving you differing bond angles. Okay?
2 electron pairs repel each other to opposite sides of the central atom 180 degrees apart. This arrangement of electron pairs is called linear. An example of a molecule with linear geometry is beryllium fluoride.
Okay, so that was an example with 2 non-bonding or 2 bonding pairs. Sorry. All right, so now on the next one we're going to look at 3 electron pairs.
3 electron pairs repel each other to the corners of an equilateral triangle, 120 degrees apart. This arrangement of electron pairs is called trigonal planar. An example of a molecule with a trigonal planar geometry is boron trifluoride.
Okay, and then the next is 4 electron pairs. Okay, all of these, of course, are bonding.
4 electron pairs repel each other to the corners of a regular tetrahedron, 109.5 degrees apart. The tetrahedral arrangement of electron pairs gives the greatest distance possible between the electrons in 3-dimensional space. An example of a molecule with tetrahedral geometry is methane.
Okay, and one more video clip showing, I believe it's got 5 electron pairs.
Iodine pentafluoride has a lone pair of electrons on the iodine atom. The 5 bonding pairs and 1 non-bonding pair form an octahedron. Since there is no atom at the lower apex of the molecule, the shape is square pyramidal. This final view shows a space-filling model of the iodine pentafluoride structure. The purple sphere represents the iodine atom, and the green spheres represent the fluorine atoms.
Okay, and you should have noticed that lone pair at the bottom has a greater repulsion. Right here. Okay? All right, so that's just a few examples. And remember, now I will insert a clip after this video to show what are bonding pairs and another way of counting bonding pairs by just calling them electron domains. Okay, in this little lesson here, in this clip, I'm going to show you how to determine the shape of the molecule. Okay, so before we start looking at the shapes of the molecules, we should talk about what are called electron domains. Okay, and so this is a little generic formula for a central atom having 1 or more atoms bound to it. Okay, so we're determining the shapes of only these kind of molecules, okay, or ions. All right, so now what is an electron domain? An electron domain is just an area around the central atom where you will find either a lone pair, a bonding pair, 2 bonding pairs, or 3 bonding pairs. So a single, a double, or a triple bond. It's just an area. Okay, so that's 1 electron domain. That's considered 1 electron domain. that's considered one electron domain, and this is considered one electron domain. It's just an area about the central atom. Okay? All right, so let's start. Okay, so here's an example of carbon dioxide. Okay, it has carbon in the center, oxygen bound to it, and it has 2 electron domains. Okay, so if you think about it, technically there tends to only be 1, 2, 3, 4 domains around a central atom. But we do have elements in our periodic table that do break the rules. Remember when we were drawing Lewis structures, okay, we saw some molecules having more than an octet around that central atom. Okay, so that's why you want to be able to count the domains. All right, so in this example there is 2 electron domains, 2 total domains. Okay, now both of these are bonding domains, and so none of them are non-bonding. Okay, so what shape is this? Well, if the molecule has 2 bonding domains and no non-bonding domains, the shape is going to be linear. And remember what I said earlier. The only way to understand this is to practice and begin to memorize. Okay, it just starts to get locked in. Okay, and then there's the bond angle of 180. Okay, here's an example of an ion. This is the nitrite ion. Okay, so here's the Lewis structure. So let's count the total number of domains. 1, 2, 3. 3 total domains. 2 of them are bonding, and 1 of them is non-bonding. Okay, so what is that molecular shape? Well, remember, there's really nothing here if we were building the molecule with a molecular kit, so we would have what is called a bent shape. Okay, and remember, you just want to understand the angle is going to be less than 109.5. All right, here's another example. Okay, this is methane. 1, 2, 3, 4 electron domains. 1, 2, 3, 4 bonding. 0 non-bonding. What do we have for a shape? Tetrahedral. Hopefully I can spell that. Okay, a tetrahedral shape. Bond angle 109.5. Okay, here's another one. 1, 2, 3, 4. So while there's 4 electron domains, just like the previous example, we don't get a tetrahedral shape because this lone pair repels more than the bonding pairs can. So this becomes less than 109, like the tetrahedral, because there's a greater repulsion there. So 3 bonding, 1 non-bonding. What do we have for a shape? Trigonal. I always say pyramidal, but basically that's what it is. It's a pyramid, but it's trigonal pyramidal. Okay, so there's another example. All right, so now let's start breaking some of the rules. Okay, and let's put a sheet underneath here so that we don't leak through there, in case we want to review that. Okay, so now here's phosphorus. Phosphorus is able to break the octet rule because it has that d orbital. Remember when we start in the periods where the d orbitals can begin, we have the ability to break the octet rule or have a greater than 8 electrons. Okay, so here we go. So let's count domains. 1, 2, 3, 4, 5. So that's 5 total domains. Okay, how many of them are bonding and how many of them are non-bonding? Okay, so they're all bonding. No lone pairs, so we have 0. So what do we have for a shape now? Okay, we have trigonal again. Trigonal, sometimes you might hear them say, but this time it's bipyramidal. Can I spell that? Pyramidal. Okay, all right, here's another one. and you're going to see this one in concept check at the end of the video or towards the end of the video, so you may come back and reference this one again. Okay, so let's count domains. 1, 2, 3, 4, 5, 6. So this time we have 6 total electron domains. 4 of them are bonding and 2 of them are non-bonding. So what do we have for a shape this time? Okay, 4 bonding, 2 non-bonding. Okay, this time we're looking at square planar. Okay. Square planar. Now if I could draw better, if I could draw three-dimensionally, I could draw that out so you could see that a little better. But in class, I'm going to give you a handout that shows all the different examples of the different shapes broken down based on the number of total domains and then bonding and non-bonding domains. And so what we'll do is we'll work with that handout for a while so that we start to get used to trying to determine the shapes. Okay? And then we'll try and put the handout away and practice with just what we know. Okay? So remember, electron domains are just areas around the central atom where you can find electrons. So it's just the whole chunk. Even though there's 3 sets of pairs here, it's still considered one domain. Okay? 2 sets of pairs, one domain. 1 set of pairs, one domain. Lone pairs, one domain. Okay, and so you count them all the way around the central atom. Okay. Okay, here's a concept check. So can you draw the Lewis structure and then determine the shape of the molecule and then see if you can figure out the bond angle based on the shape. Here's the answers to the first concept check. Okay, so hydrogen cyanide, I'm going to draw the Lewis structure first. So I've counted 1, 4, 5, a total of 10 valence electrons. Okay, H connected to C, connected to N, the least electronegative in the center. Hydrogen can't be in the center because it can only have one shared pair. And so it has to be the carbon atom this time. So we've used 4 electrons so far. So I've got 6 left to place. We place them on the outer atoms first. Hydrogen already has its total pair, so it can't hold anymore. So all 6 of these have to go on this outer atom. All right, so now I've used all 6. I have no more electrons left. Happy, happy, not happy. Okay, so what do? We have to push a pair down in between. Okay, and that makes nitrogen still happy, but carbon not happy yet. So we got to push one more pair. So we end up with hydrogen, carbon, triple bond, 1 pair left. Okay, so what kind of shape do we have? Well, we have 2 total electron domains. Okay, 2 bonding, 0 non-bonding. So what do we have for a shape? Linear, 180 degrees. Okay, here's the next one. Phosphorus trihydride, 5 and 1 for a total of 8 valence electrons. Okay, so 1, 2, 3, we got a H, H, H. 2, 4, 6, we've used up 6 electrons. We've got 2 electrons left. Any remaining electrons go on the central atom. All right, what do we have? 1, 2, 3, 4. 4 total domains. 3 bonding. 1 non-bonding. Okay, now remember that lone pair pushes more. So what do we have? Trigonal, pyramidal. Okay, and let's see, what is that degrees? Less than 109. So almost put a percent. Less than 109 degrees. Okay, let's try another one. Sulfur tetrafluoride. Okay, 1, 6, and then 7 for a total of 34 electrons. So let's go 1, 2, 3, 4. Put our F's on there. 2, 4, 6, 8. I've used 8. I'm left with 26 electrons, if I can subtract correctly. And we put our octets on our outer atoms. So 2, 4, 6 times 4 is 24. So that leaves me with 2 electrons left over. They would go on the central atom. So let's count our domains. 1, 2, 3, 4, 5 total domains. Okay. Electron domains. 4 of them bonding. 1 non-bonding. So what do we have for a shape? We have a seesaw. So it really kind of looks something like this. F, F. If I could make this come out the side, F, and then our F down, and then our lone pair. Okay, and that's called a seesaw shape. All right. And so I believe the angles were 90 and 180. Okay, so there's the examples from the concept check. Okay, hydrogen cyanide, phosphorus trihydride, and sulfur tetrafluoride. Okay, so stop the video, try it, then I'll pull up the answers, and then I'll insert a video clip to show you how to get those answers. Okay, linear, 180 degrees. Trigonal pyramidal, 109.5, well, less than 109.5 technically because of the lone pair. And then seesaw. Okay, hopefully that went well. Again, I'll insert a clip here now. Okay, another concept check. Can you determine the shape for ozone, O3, and its bond angles, and krypton tetrafluoride, shape and bond angles? Remember, stop the podcast, you try it, and then check your answer. Here's the second concept check. This is ozone. Okay, so as I draw this, I need my valence electrons, 6, 6, 6. Woo! All right, so let's connect them. 1, 2, 3. So I've used 2, 4 electrons so far. I have 14 electrons left. Okay, I start fulfilling the outside. 2, 4, 6, 8, 10, 12. Okay, I got 2 electrons left. They go in the central atom. All right, so it looks like 2 of the 3 are content with their octets fulfilled. Center not content. So what we have to do is take a pair and push it in between. Okay, so we end up with our 1, 2, 3, 4, 5, 6. 1, 2, double bond, 1, 2, 3, 4. Now remember, we learned in the last lesson resonance structures, which simply mean it's a blend of both. So we draw both possible drawings. Okay, 2, 4, 6, 8. All right. And so this is the Lewis structure for ozone. I count 1, 2, 3 total domains. All right, 2 bonding and 1 non-bonding. So what do we have for a shape? Remember, that's going to push greater than the lone pairs, than the bonding pairs. And so you're going to have a bent shape. Okay, and that bent shape is going to be less than 109.5. Okay, and so there's your ozone example. And then here's krypton trifluoride. And so let's see, we need to get our valence electrons. Krypton is in group 8A, so 8. The fluorine atoms are in group 7A, so 7. So 7 plus 7 plus 7 plus 7. So 7 times 4 is 28. 28 plus 8 is 36 electrons. So we're dealing with 36 electrons. Okay, so we start drawing our structure. Central atom connecting the outer electrons. 2, 4, 6, 8. I've used up 8. So I'm left with, let's see, 28 electrons. Okay, so let's fulfill the octets on the outer atoms. So 6 times 4 is 24. So I've got 4 electrons left. Any of the remaining electrons go on the central atom. So there we have it. How many domains? 1, 2, 3, 4, 5, 6. 6 electron domains total. I see 4 bonding and 2 non-bonding. And so what do we have for a shape? Square planar. Okay, what are we going to have? We're going to have 90 degrees between the bonding pairs and 180 between the non-bonding pairs. So I guess we're just going, I think we just would discuss the 90, not the 180. But anyway, as you begin to visualize these, as we play with the molecular kits, you'll get a better feel for these structures. Okay, bent, 120. Square planar, 90 and 180. And another concept check. Molecule that has polar bonds will always be polar. True? Why? False. Why? Okay, and the answer, of course, is false, because just because something has polar bonds doesn't mean it will be polar. You also have to check the geometry. And that's the purpose of understanding this model, so we can determine whether a molecule is polar or not polar. So for example, carbon dioxide. You've drawn carbon dioxide once already as Lewis structure practice. You've seen it in this video clip. They've used it in some of the videos. And CO2 contains polar bonds. You can check that out by subtracting the electron negativity values and finding out that the bond is polar. And then it's going to be nonpolar overall because it's linear. So it's symmetrical about that central axis. And so in essence, those charged ends have a canceling effect. And so the molecule ends up to be nonpolar. Okay, another concept check. Lone pairs make a molecule polar. True? Why? False. Why? Okay, and so that answer is false. At times, if there's only one set of lone pairs, it can make the molecule polar. But if there's two sets, then the molecule is not necessarily polar. For example, xenon trifluoride. This one was drawn in a video clip earlier, and it contains two sets of lone pairs, and therefore that makes the molecule symmetrical about the both axes, and so the molecule ends up being nonpolar. Okay, now this may seem to be a little overwhelming, but the trick to understanding the molecular geometry is you have to just practice, and then as you practice, you visualize these different structures, and then you just begin to memorize them. And that's the only way to work with this. So you just got to spend some time practicing and then memorizing. Okay? And so these diagrams are in your text, and so you should reference them. Okay? And you want to be able to determine the molecular geometry and the angles in the molecule. Okay, here's some structures that have both bonding and non-bonding pairs. When you see these structures, this is the s orbital, this is the this is the p orbital, this is the s orbital. Remember, the s orbital is spherical, the p orbital is dumbbell shaped. Okay, and so that's a bonding pair right there. And in chapter 9, we'll begin to talk about what's called hybridization, and that's what happens when your s orbital here and your p orbital come together. So this is an example of all bonding pairs. And here's an example. This is a non-bonding pair. This is a lone pair here. And the greater repulsion causes it to be pyramidal in shape. Okay. And now in this example, there's two non-bonding pairs. And so greater repulsion causes this bent shape with a smaller angle than 109, which is the tetrahedral up here. This is 109.5, and this bond angle will be smaller than that, like roughly 105. But I think for your beginning understanding of these angles, if you just remember it's smaller than 109.5, that's enough understanding to give you credit. And so this is the lesson on the Vsepr theory. And like I said, now in our next lesson in chapter 9, we're going to be talking about hybridization.